how do you interpret them? What do they do? Well, they're variables, right, in a grammar, and so from them you can derive strings, right? That's what you do with a grammar. That's what variables are for. So this particular, like AAPQ, it will derive a set of strings. So we want this AAPQ to derive all the strings X that the PDA would, if the PDA starts in state little p and it reads through the substring X and finishes in the state little q, then all those substrings where the PDA starts in state P and ends in state Q, all those strings, being read by the PDA, are the same set of strings that this generates, that this variable generates in the grammar. Okay? So if that happens, the two things, the machine and the grammar, are behaving in the same way. They're equivalent. Right? So what I've just said is fairly important in the last few sentences. Okay? So rewind if necessary. Okay? Now think about it. If this is your start variable, you're starting in the initial, the start state of the machine, and this is an accept state. So this variable, what set of strings will it recognize? Well, all those strings X that start in that state and end in that state for the machine. Well, all those strings, well, that's the language of the machine, if you think about it, right? Because it's like all the, it's the full X, it's not the substring, it's the whole string. So all the strings that this generates should be the same as all the strings that the machine recognizes. Okay? Right, now here are the rules. Now it's not obvious, but when you get into the proof and you see the details of the proof, you'll see the motivation for the rules, hopefully. Now you need to study both, and I keep saying, go back and forth, so that you see how the functioning of the PDA is motivating your choice of rules. And states and variables for the grammar. Okay, so now you've got deltas here. A delta, that's the transition function, right? Transitions. Well, that's PDA. Right? That's an automaton. You transition from state to state. Okay, so that's PDA language. So you go looking in your PDA, and you have a look at the transition rules in the PDA, and if this particular transition rule now remember, it's a non-deterministic PDA. Remember, strictly speaking, the proof of equivalence is between a context-free grammar and a non-deterministic PDA. Okay. Now, non-deterministic PDAs, their transition functions, they will output a set of ordered pairs. Okay. So that set will contain members. So if one of the members is this one for that transition rule, and another ordered pair is a member of this transition rule, then add this rule to your grammar. Okay? So you go checking in the PDA. You look for this transition rule and this transition rule, and if this one contains that ordered pair and this one contains that ordered pair, then put this rule into your grammar. Okay. Now let's go into detail. What's going on here? Now remember the order of these three parameters, I guess, in your PDA transition rule. Remember the first one is the current state of the PDA. So that one's the state. This second one is the input string symbol currently being read. Right? And the third one, that is the symbol at the top of the stack at that moment. Okay? So if you have a transition rule of this form, the PDA is in state little p, it's currently reading little a in the input stream, and this you interpret that to mean ignore what's on the stack. So don't look at the stack, don't push it or pop it or just ignore it. Okay? So in other words, if the states if the PDA is in state little p and it's reading the symbol a, and the ordered pair that transition rule returns, if one of its members is this one, now how do you interpret this? Well, remember the ordered pair in a PDA, the first one is the next state. Okay, it's an automaton. It'll go to the next state. So little r here is the next state. So it'll go from P to R, right? And what's T? Well, that's a string. Now remember the shorthand, we're talking last board. That T is a string that gets pushed onto the stack, right? So if these three, or actually two things are valid at a given moment in the PDA, then switch from state P to R and push T onto the stack. Alright. Okay, now similar logic with these. So you go looking for a transition rule in the PDA, and you have a look at this, and if what this thing returns in that set, if this is one of the members of that set, now what are we talking about? So we're in state S now. We're reading a B on the input stream. T, wait a minute. T, oh okay, we're being strict. Okay, T is a symbol. It's not a string. Well, the symbol's a string, but it's a one symbol string. And T is on the symbol that's on top of the stack. Then have a look at what this returns. The set of ordered pairs. Now, if one of them in that set, one of the members of that set is this ordered pair, Q, epsilon, how to interpret this? Well, the next state is Q. So in other words, you go from state S to state Q, and you ignore the stack. You don't do anything with the stack, right? Now, okay. So if those two things, so if this does contain that and this contains that, then put this rule in your grammar. And you may ask, what the hell? Why? Where'd that come from? Well, you won't see the motivation until you get into the proof. That's why I keep saying, go back and forth, right? So, okay, so you put this rule in your grammar. Your grammar. Your C of G. Okay, you now have this, and do that for all four possibilities. So. That's going to be an awfully large number of these sort of rules. Okay. Okay. Also, for all P, Q, and R, these are all states belonging to your PDA. Put this in your set of rules in your grammar. Right? These. And remember, these A's, they're variables. So actually this variable here, this rule here is in Chomsky normal form, if you think about it, because you've got two variables. Okay. And finally, for all states belonging to your PDA, okay, put in this rule into your grammar. So APP goes to arrow epsilon. So, all right. So look at your PDA, because that's given, right? We're trying to construct a grammar. The work we're doing is on the grammar. We're trying to create a grammar that behaves like the PDA. The PDA is given, right? With all its transition function, all that's given. So this here, do all this work. Build the grammar. Build the states of the grammar and build all its rules, its substitution rules. And this is the recipe. Like here's the algorithm. So go checking, for all PQR, go checking if this contains that and this contains that. If so, then put this substitution rule into the grammar. For all possible cases. And similarly for here, all possible cases. So you'll end up with a lot of transposition rules, substitution rules in your grammar, right? Now assume we've done all that work. Now we can start with the proof. Okay. Now okay. So. What are we trying to show? This is given, right? We're told that this variable, and you've got n squared of them, let's say. So now if this variable generates x, in other words, you can derive x from this variable, okay? Then that same x, what is x? Well, it's just a string of symbols. Right? That same x, when you put it into the machine, the automaton, where the machine is in state little p, then the machine will end up in state little q, and in both states with an empty stack. And that's what we're trying to prove. All right. Now we're going to use induction, so let's. We'll start, it's always a two-step. Start with the basis and then the inductive step. So we'll do with the basis. So let's assume the derivation, from going here to here, that we just have one step. Okay? Now, so you go directly from this to that. Now, this x here